Okay, welcome everyone. Today we're doing a deep dive into getting things ready, making absolutely sure critical equipment is good to go before it starts its real work.
That's right. And our guide for this is something really practical, not a big study, but an actual pre-commissioning checklist, specifically for submersible pumps.
Ah, so like a pilot's checklist, but for underwater machinery.
Exactly that. It's a very ground level, very detailed.
And that's what we want to unpack, right? Use this checklist you shared to really understand the prep work involved. What does it take to make sure these pumps are reliable right from the start?
Well, the list, it kicks off with the fundamentals, just ensuring the pump's physical state is okay.
Like a visual check, does it look all right? No damage from shipping or putting it in?
Precisely. But then, interestingly, it immediately has you check for unusual noise.
Noise. Before it's even properly running. What could that tell you already?
Oh, quite a bit potentially. Maybe bearing problems or something rubbing inside, like the impeller. It's about catching internal issues really, really early.
Okay, wow. Early detection.
And linked to that physical state is leak tightness. The checklist mentions it a few times. General leaks, valve leaks.
And specifically non-return valves, too. Why the focus on those for leaks?
Well, a non-return valve or check valve should only let water flow one way. If it leaks backwards,
You get backflow.
exactly, which can mess up system pressure, efficiency, or even drain the line when the pump stops. That can cause issues like water hammer on the next startup. For a submersible, any unexpected water movement is usually bad news.
Right. Definitely don't want water going the wrong way underwater.
hmm
Okay, it also mentions inspecting anti-vibration blocks. So not just the pump itself.
Yeah, the mounting matters too. Those blocks basically isolate the pump's vibration from whatever it's attached to the foundation, the structure.
Because pumps vibrate, I assume.
Oh, they do, especially the big ones. Without that isolation, you get noise, fatigue, potential damage to pipes, electrics. Checking ensures that buffer is working from day one.
Makes total sense. Then it seems to shift to mechanical harmony, checking motor and pump alignment, the coupling. Why is that precision so vital?
Misalignment is probably one of the biggest reasons pumps fail early. If those shafts aren't perfectly lined up, it puts massive stress on bearings, seals, the coupling itself.
Just wears everything out much faster.
Much faster, creates vibration, eats up energy. Checking it before running stops that wear starting immediately.
Hmm.
They also check the guide rail installation, that's how the pump slides down, and the inertia base, if there is one.
An inertia base, what's that doing?
It adds mass, basically. And rigidity. Helps absorb even more vibration, provides a really stable platform, especially useful for bigger pumps.
Stability, smooth running.
Yeah.
That sounds like lubrication would be important too.
Spot on. The checklist calls out lubricating bearings, motor, and pump, and then a general double check. It's fundamental.
Fundamental how?
Well, without the right lube, you get friction, heat, wear, parts degrade fast. You could end up with seized components, total failure, simple step, huge impact if you miss it.
Okay, got it. Then there's the electrical side, the lifeblood for the motor, checking protection overload relays, verifying voltages connections.
And crucially, confirming the motor's rotation direction.
Why is rotation direction so critical to check beforehand?
Well, running a centrifugal pump backwards, it doesn't pump well, obviously, but it can also damage the pump, maybe overload the motor. You need it spinning the right way from the first second.
Makes sense. Now, what I found really interesting were the control checks before full operation, like verifying dry run protection float switches and auto hand control float switches, checking the wiring from the tank to the panel. Why so early for controls?
Because those are your safety nets and your operational brain, really. A
Mhm.
submersible pump has to stay submerged. Run it dry, the motor burns out fast.
Ah, so the dry run float switch prevents that.
If it's working correctly, yes, it should shut the pump off if the water gets too low. If you don't check that before it's needed, the first time the level drops, well, you could lose the pump.
And the auto hand floats.
They manage the normal on-off cycle based on water level. Making sure they're right ensures the pump runs automatically as designed, safely. They're like the system's eyes. Checking them early stops costly mistakes right at startup.
So looking back at this checklist, it's this clear, methodical path, isn't it? Physical integrity first, then mechanical precision, then correct power and protection, and finally, verifying those critical controls and safeties like the floats. It's incredibly detailed.
It really is. And, the systematic approach, checking everything layer by layer before you go live, that's not just for pumps. It's a core principle for almost any complex system you can think of.
Right. Methodically checking everything first drastically cuts down the chance of early failures.
Yeah.
ensures reliability.
Exactly. It helps guarantee performance right from the very beginning. It's about preventing problems before they even have a chance to start.
It really makes you appreciate that level of detail. So, thinking beyond pumps then, what other areas in life, maybe something completely different, do you think could really benefit from that kind of thorough step-by-step pre-commissioning before jumping in?